this video I'm going to be dealing with rational exponents. I am specifically making the video for the Math 105 class at IUK, and in their textbook this is section 7-2. However, anybody that would be dealing with rational exponents could benefit from this video as well. I do want to make a note that this is part 1 of 2. In this video I'm going to go through the definitions or the rules that were in section 7-2 with some examples after each definition, and then in the second video just simply work out several different examples where you're putting all of these different rules and definitions into play. Okay, so for our first definition here, I've got a to the 1 over n, and that can be rewritten as the nth root of a. Okay, this is going back and forth in between rational exponents and radical form. Alright, and it works going both ways. So just some examples to work through how this definition would work. Alright, let's say it says use radical notation to rewrite the expression, simplify if possible. Okay, so if I had 64 to the 1/2, alright, so 1's on top, 2 is the denominator there, so that means that's going to be my root. So this would be the second root, or the square root of 64, and I can simplify this. Square root of 64 is 8. Okay, so again here on this one, I've got in parentheses a negative 125. Okay, so that means that's my entire base being raised to the 1/3. So it's going to be the third root, the cube root of negative 125. And if you recall, you can take cube roots of negative numbers. So that's going to be a negative 5. And here again in this last example here, my entire base is indicated as the 6x squared y because of the set of parentheses there being raised to the 1/5, which means it's going to be the fifth root of that 6x squared y for the whole entire thing. Okay, so real easy implementation of that rule. Alright, now let's show the rule going the other direction. Okay, how about if it said rewrite with rational exponents and they gave it to you in square root form, 5th root, 7th root. Okay, so this would be the 5th root of 13ab, and that's all to the first power. Alright, so I would rewrite as 13ab, that being my entire base because the entire thing is underneath the radical, and then raised to the 1/5. Okay, and then same thing over here. This entire thing right here has raised to the first power right there. It's the 7th root. So since that's the entire base, I would write x y squared over 17 raised to the 1/7 power. Alright, so implementing that first rule both directions. Okay, now the second definition that we're going to do is pretty much the exact same thing, except it's not going to have a 1 in the top. This rule also works for any fraction, so m over n. The denominator is always the root. The numerator is what's being raised to. Now, on this one, we could place it a couple different ways. Alright, I could do the nth root of a and then raise it to the nth power. Or I could do the nth root of a to the m. Alright, now this one I would venture to say you're not going to use very often, because as soon as you go a raised to the m power, that becomes a very, very large number, which then makes taking the nth root a little more challenging. So if you take the root first and then raise it to that exponent, it allows you to do the math probably a little bit easier and do it in your head definitely without probably a calculator. Alright, some examples of this. Alright, the directions might say use radical notation to rewrite each expression and simplify. So then they might give us 1,000 raised to the 2/3. Okay, so now you've got to remember that bottom denominator is going to be the root. So this is going to be the third root of 1,000 and then squared. Alright, and this is very definitely going to be easier to do it this way than if I tried to take 1,000 and then squared it and then take the cube root. I'd have a really big number. Don't want to do that. Okay, cube root of 1,000 is 10, and I still have to square it. 10 squared is 100. Okay, now on this one right here, alright, you kind of got to be careful on what the actual base is. The actual base of this is really 32. Alright, there is no set of parentheses. It is not negative 32. If I rewrite over here, negative 32 to the 3/5. Alright, really technically there's an imaginary negative 1 that's sitting in front of it. So my only base here is the 32. Okay, so that means I'm going to have negative, and then my root will be the fifth root of 32, and then I want to cube it because it's going to be easier to find. Okay, so the fifth root of 32 is going to be 2. That negative is going to be out in front. And then I'm going to raise it to the third power. 2 to the third power is 8, so I'm going to have a negative 8. Alright, now going the other direction with this rule. Okay, what if it tells you to rewrite with rational exponents, and this time they're giving you cube root or fifth root with a power involved there. Okay, now this root is always the denominator, and that's the numerator, so rewriting this with a rational exponent would be 6 raised to the 4/3. Alright, and then this one, the fifth root there would be my denominator of the fraction, the 7 would be the numerator. So I'd have a 2xy raised to the 7/5. Okay, so that rule implemented. Alright, now we've got one more rule that we want to take a look at here real quick. This one kind of follows along with your laws of exponents. Alright, let's say I've got a raised to the negative m over n. Alright, if you recall just from a regular negative exponent, we can move it to the bottom. Alright, and make it positive. Alright, which I need to, whoops, get my white out there and take that off there right there. Alright, if you've got a negative exponent like this and you move it to the bottom, then it makes your exponent positive. So an a raised to the negative m over n would be 1 over a raised to the m over n, the positive m over n. So in this example right here, rewrite each expression with a positive exponent. So they're telling you what to do. Simplify if possible. Okay, so this entire expression is going to get moved to the bottom. I'm going to have a 1 on top, and it'll be a positive 3/5. Alright, now it does say simplify if possible, so then now I've got a rational exponent here, and with our last rule we learned that this could be the fifth root and then raised to the third power. So I'm going to have a, I'm going to go sideways on this one I think, 1 over the fifth root of 32 cubed. Alright, now fifth root of 32 is a 3, or fifth root of 32 is 2, so I'm going to have a 1 over 2 to the third, and 2 to the third is 8, so then I'll have a final answer of 1/8. So that's kind of implementing this rule first, and then using the previous rule to simplify and go a little bit farther. Okay, so on this one, I need a positive exponent first, so I'm going to apply this rule up here first. So I'm going to go 1 over a 125 to the 1/3. Makes it a positive 1/3. Alright, now it says simplify if possible, so now I'm going to make this the third root. So the third root of 125. Alright, and then to the first power. I don't need that there. And now the third root of 125 is 5. So it simplifies down to a 1/5. Okay, so basically this is your 3 definitions that are in the very beginning of section 5-2 for those students that are in Math 105 at IUK. Alright, however, there are 3 basic rules that deal with rational exponents for anybody. Alright, the part 2 video is going to take all of these rules, and we're just going to do lots of examples implementing these to be able to simplify problems. So definitely thanks for watching, and be sure and share with your friends. Thanks. In this video I'm going to be talking about rational exponents. I am specifically making this video for the Math 105 class at IUK, and it covers their section 7-2. However, anybody that would be working with rational exponents, everything that I say is going to be applicable to you as well. Alright, and I might make a special note that this is part 2 of 2 videos that kind of go together. In the first video I went through 3 specific definitions of how you deal with rational exponents with some examples for each one of those, and then in this one we're going to just review a little bit of our laws of exponents and then just kind of put everything together from both videos and how to simplify problems. Alright, to start with, you've got to be able to know your laws of exponents. You initially learn these with integers for the most part as your exponents. All of those exact same rules apply if you have a rational exponent. So just real quickly to go over those rules again, when multiplying like bases we add the exponents, so that's what this rule shows right here. If you've got a base that's raised to an exponent that's raised to another exponent, power raised to a power in other words, you multiply those two exponents. Whenever you are dividing bases, then I can take that exponent and put it to both the numerator and the denominator, so that would be an a to the n over b to the n. If I'm dividing like bases, I can subtract the exponents, which is what that rule shows right there. And then this one is, if I am multiplying a variety of things, then I've got to remember and take that exponent and multiply it by both of the exponents that are on each of those bases, so that would make this an a to the n, b to the n. Alright, so that was just a real quick review of just your basic laws of exponents, which you're going to have a command on, a good command on, to be able to do rational exponents with this. Okay, so 3 little examples of where we're just dealing with rational exponents. Okay, suppose the directions say no more than simplify. Alright, you see those rational exponents floating around different places. Alright, so you just kind of look and see which kind of rule are you looking at here. This is when multiplying like bases. So when multiplying like bases, add those exponents. So 1/7 and 4/7 is a 5/7. So 6 to the 5/7. Alright, and it doesn't say anything about going any farther than that. We can leave our answers as these rational exponents. Okay, now this one I am dividing like bases. So when we divide like bases, we subtract those exponents. Alright, now those coefficients, we're going to treat those just like regular numbers. So we're going to go 32 divided by 16. Alright, that's going to give me a 2. When I divide those like bases and subtract the exponents, I'm going to have the same like base. Alright, 1/2 minus 3/4. You've got to do it in that order. That's going to give you a negative 1/4. Okay, and then from the first video we learned how to get rid of negative exponents. Basically all you have to do is move them to the denominator. So in this case, this x to the negative 1/4, this is going to get moved to the denominator, but that 2 is going to stay in the numerator, that coefficient. So then I'm going to have 2 over an x to a positive 1/4. And then here in this last example, this is an example of power raised to a power, but with 2 bases inside and 2 sets of exponents there. So on this one, you've just got to remember that that 1/2 has to be multiplied by the negative 2/5. It also has to be multiplied by that 1/3. Okay, so then that's going to give me an x to the negative 2/10 and a y to the 1/6. Okay, now anytime you end up with a fraction that can be reduced, probably need to go ahead and reduce that. Okay, so then I'm going to have an x to the negative 1/5 and a y to the 1/6. Alright, and now I'm to the place where, okay, I've got a negative exponent, so just like we had with this negative exponent up here, we moved it to the bottom. Okay, so that's the only thing that's going to get moved to the bottom. Alright, so then the y to the 1/6 is going to stay in our numerator. So y to the 1/6, moving this to the denominator, making it positive x to the 1/5. Alright, so 3 nice little examples there, just kind of reviewing those laws of exponents and dealing with them as rational exponents as opposed to integers. Alright, now we need to get to where we're using everything in both these 2 videos that I've made, and you're just going to apply everything to simplifying these higher level radicals. Alright, the directions are going to be very specific. They're going to say use rational exponents to simplify. Alright, this is just a method of how you can simplify higher order radicals, and it makes sense, and especially when you've been working with those rational exponents for such a long time. We are going to assume that all variables represent non-negative numbers, so we're not going to deal with any absolute values or anything. Okay. Alright, so for this one, I'm going to rewrite this using my different rules that I've shown in the 2 videos. Now, I'm going to look at this very carefully before I start. The cube root of 27. Alright, well, the cube root of 27 is 3, so I'm definitely going to just want to separate these into 2 separate things, because my 27 is being multiplied by that x to the 15th. So if I do the cube root of 27 and just leave it, since I know that I can answer that out, then on this x to the 15th, and it's the cube root of it, rewrite that in fraction, with an exponent, so x to the 15 over 3. All right. And like I said, this is probably the easiest because the cube root of 27 just gives you a 3. And then now I can take a look at that rational exponent right there. 15 divided by 3 is a nice little 5. So then x to the 5th. All right, it just makes a really nice, simple way to simplify these radicals. All right, now on this one, I've got 2 in here. Now, technically, depends on, if you want to show absolutely every step. I think I will show absolutely every step here. Technically, everything in here is to the first power. All right, so then when I take this and turn it into with a rational exponent, rewrite it like that, I'm going to have an x to the 4th, a y squared, and that's going to be raised to the 1/8 power. Okay, now, implementing those rules for rational exponents means I've got to multiply that 1/8 by both of those exponents in there, and then I'm going to have an x to the 4 over 8 and a y raised to the 2 over 8. Now, a lot of people can go straight from this step to this step without putting this extra step in there, because you can just tell that that's going to be an exponent of 1, so it makes it really easy. 4 over 8, 2 over 8. So either way, you can leave that step out right there. All right, now both of those two fractions I can reduce, so I'm going to go x to the, let's go ahead and leave it 2/4 because I want my denominators to stay the same, so then I can do like a 4th root. Okay, let's rewrite this with a power of 1/4. So if I did that, then I'd have an x squared y raised to the 1/4. Now that I've got that, now I can do the 4th root. So 4th root of an x squared y. And as you begin to do more of these, you're going to realize, oh yeah, if I've got the same bases on here, this is going to make it a whole lot easier when I go to pull things out like that. Alright, now you could encounter a problem that has, like a cube root and then a square root, nested radicals like that. I would recommend working on the inside first and then see what we've got. So I'm going to leave the cube root alone, and I'm just going to change that inside one to x to the 1/2. Alright, now, depending on how many steps you want to show here, alright, if I think of it like this is being raised to the first power, so then I can rewrite this as an x to the 1/2 raised to the 1/3, and now I've got power raised to a power, so then I've got an x to the 1/6, and since we are trying to simplify the radical, we'll put it back in radical notation here, 6th root of x. Okay, and granted, this is, some of you are going to be able to get to this a lot quicker, alright, but if the directions actually want you to use those rational exponents, then you need to show that work to see how you got to that 6th root of x. Okay, let's do 2 more examples, just trying to encounter as many of those different laws of exponents that I can here. Alright, so let's do the 6th root of 2x raised to the 4th. Alright, so on this one, everything there is my base, so then I can rewrite as 2x raised to the 4 over 6. Alright, let's take that fraction now and reduce it. So 2x raised to the 2/3. Okay, now I'm going to implement the power raised to a power. Both those have 1s, so when I multiply by each of those, I'm going to have 2 to the 2/3 times an x to the 2/3. Alright, now I need to go into radical form with this one. So this is going to be the cube root of 2 squared. So cube root of 2 squared. And then this one's just going to be the cube root of x squared, which we can't do anything with. Alright, this one I can multiply out. 2 squared is going to be 4. They both have the same radical there, so I can write it as one radical, cube root of 4x squared. Okay, so lots of different rules on that one being implemented. Okay, now on this last example, alright, again, how many steps do you want to put in there? Okay, if you want to put a parentheses around this with a 1 and put a parentheses around that with a 1 and have that extra step, you can. You'd have that power raised to a power. If not, and if you're getting a little bit better at this point, then you can just automatically go to a x to the 5/4 and a y to the 5/4, all over an x to the 1/2 and a y to the 1/2. Alright, now I'm dividing like bases, so that means I've got to subtract each one of those. 5/4 minus 1/2 on both of them will be the exact same thing. So then I'm going to have an x to the 3/4 and a y to the 3/4. Alright, and both of them already having that fourth root there, so then I can go the fourth root of x to the third, y to the third. Alright, so just several examples here in this second video trying to implement all of the different rules that you're shown in section 5-2 for the Math 105 students. Alright, and in general, just how you can use rational exponents to simplify higher order radicals. Definitely thanks for watching, and be sure to subscribe to the channel. Thanks.